Within the framework of the International Materials Research Congress 2025, we present a work entitled Chemical Synthesis and Characterization of Zinc Oxide and Zinc Oxide with Tin Oxide for Use in Photocatalysis. In this study, we present a comparative analysis of two zinc oxide-based nanomaterials synthesized via a straightforward chemical precipitation method, zinc oxide with tin oxide core shell structures, in which a zinc oxide core is coated with a tin oxide shell, and zinc oxide with tin oxide nanocomposites. Zinc nitrate, tin chloride, and sodium hydroxide were employed as precursors under controlled conditions. Structural, morphological, and chemical properties were investigated through X-ray diffraction, scanning electron microscopy, energy dispersive X-ray spectroscopy, and UV-vis spectroscopy. XRD confirmed the Wurtzite structure of zinc oxide, while the presence of tin oxide was observed in both systems. SEM imaging and EDS elemental mapping revealed clear morphological distinctions and characteristic elemental distributions consistent with the designed core shell and composite architectures. Optical measurements indicated subtle differences in light absorption, suggesting variations in interfacial electronic interactions. These findings provide new insights into the structure-property relationship of zinc oxide-thin oxide heterostructures and underscore the potential of tailored nanoarchitectures for enhanced performance in environmental remediation applications. Photocatalysis is a chemical process that uses light to activate a catalyst, promoting chemical reactions that can lead to the breakdown of organic pollutants and the purification of water. Currently, zinc oxide and tin oxide have emerged as promising materials in this field due to their photocatalytic properties. Zinc oxide is known for its wide band gap and high electron mobility, making it an ideal candidate for absorbing ultraviolet light and generating electron hole pairs, which are essential for the degradation of organic compounds. On the other hand, tin oxide, with its semiconducting characteristics and ability to enhance catalytic efficiency, complements zinc oxide in various applications. The combination of zinc oxide and tin oxide produces hybrid compounds that expand photocatalytic properties and enhance efficiency in converting light energy into chemical energy. Experimental details. For the synthesis of zinc oxide in a core shell with tin oxide, the zinc oxide synthesis was first carried out as follows. 9 grams of zinc nitrate were dissolved in 100 milliliters of water, a sodium hydroxide solution, 6 grams in 100 milliliters was added drop, and the mixture was left stirring for 2 hours. Precipitate was washed either or centrifugation with 120 degrees Celsius overnight. Then, the tin oxide shell was prepared. To do this, 1 gram of the zinc oxide obtained was dispersed in a sodium hydroxide solution, 1.5 grams in 50 milliliters, using magnetic stirring. 0.19 grams of dihydrated tin chloride was added, and the mixture was refluxed for 4 hours at 90 degrees Celsius. The precipitate is washed either by decantation or centrifugation with water 3 times. The material is dried at 110 degrees Celsius overnight and calcined at 400 degrees Celsius for 4 hours. Conclusions. Zinc oxide with thin oxide nanostructures were successfully synthesized via the chemical precipitation method. X-ray diffraction analysis confirmed the characteristic crystallographic planes of zinc oxide with PDF 361451. With average crystallite sizes of 394 armstrongs for the core shell and 362 armstrongs for the composite. In addition, zinc stannate PDF 24-1460 and thin oxide PDF 41-1445 phases were detected in the composite sample. UV-vis spectroscopy revealed absorption edges around 3.2 electron volts. Consistent with zinc oxide, along with a minor absorption peak at 3.7 electron volts, likely attributed to thin oxide. SEM micrographs showed unidirectional particle growth with no evidence of spherical morphologies. The obtained nanostructures exhibit morphological and compositional features that make them promising candidates for water remediation applications. The observed structural differences are expected to translate into distinct photocatalytic behaviors, offering potential for enhanced degradation efficiency in environmental treatments. Thank you for your attention.